This is section 7.3, trig substitution. The first question asks to compute the integral of 1 over x squared times the square root of x squared plus 4 dx. I think the best way to approach integrals is to decide what way you're going to analyze it, whether that be using a basic approach such as u substitution or using more analyzing methods such as trig substitution, trig integrals, or inverse trig. In this case, we would be using trig substitution because if you take a closer look at this x squared plus 4, it fits the the square root of a squared plus x squared format. And what I've done is I've written down a table of the trig substitutions that we can use. In this case, since the square root of x squared plus 4 fits the square root of a squared plus x squared format, we could say that x is equal to 2 tangent theta. So then the dx will be 2 secant squared theta d theta. It's important to always remember the d theta. I feel like I always forget to include the d theta throughout the whole problem. So from here, what you can do is you can substitute the x and dx values back into this integral. And when you do that, you should get, I'm going to put this dx up at the top just to make it easier for me to read. So I'm going to say that it's 2 secant squared theta d theta all over this x squared would be, if you squared the 2 tangent theta, you should get 4 tangent squared theta. And if you substitute the x back into this, you should get 4 tangent squared theta plus 4. And from here, I would simplify this, and then I would say that 2 secant squared theta all over 4 tangent squared theta I would pull the 4 out, and once you pull the 4 out, you should get 4 parentheses tangent squared theta plus 1, and this is all multiplied by d theta. I'm just moving it to this side just to make it easier for me to read. So then if you simplify this again, if you were to take the square root of 4, you should get 2. So then in this case, you'll get 2 secant squared theta all over 4 tangent squared theta. Pulling the 2 out, you will get 2 times the square root of tangent squared theta plus 1, and this is still multiplied by d theta. As you can see, if you can recall, you should know that the trig identity of sine squared theta plus cosine squared theta is equal to 1. And then if you readjust everything, and if you divide everything by cosine squared theta, you should see that sine squared theta over cosine squared theta is also the same thing as tangent squared theta plus cosine squared theta over cosine squared theta is 1. And 1 over cosine squared theta, if you simplify that, you should get secant squared theta. So what you can now see is that if that tangent squared theta plus 1 equals secant squared theta, if you were then to take the square root of this secant squared theta, I'll just rewrite it. So you would get 2 secant squared theta all over 4 tangent squared theta times by 2 still, and then this tangent squared theta, the square root of tangent squared theta plus 1. If you were to simplify this using this trig identity, you would get the square root of secant squared theta still multiplied by d theta. And from here, if you take the square root of secant squared theta, you should get the absolute value of secant theta. Simplifying that over, you get 2 secant squared theta all over 4 tangent squared theta times it by 2, and then you have secant theta, the absolute value of secant theta. And from here, say if I were to draw the unit circle, secant theta is also the same thing as 1 over cosine theta. And since if we look at the ranges, we can see that if we look at the domains, we can see that it goes from negative pi over 2 to pi over 2. So we're just looking at this side of the unit circle, and cosine theta is always the x value, so this will always be positive. So if we were to rewrite this and simplify, we would get 4 tangent squared theta times it by 2, and then we can take out the absolute value signs to just get 2 secant theta. If we simplify this out, we can get rid of the 2's because they're both in the numerator and denominator, and then we will get secant squared theta all over secant theta. It would just be secant theta, and then we still have I'm gonna just take the 4 out of the denominator, so this one would just give us 1/4 times the integral of secant theta, if we got rid of the 4, all over tangent squared theta. If I were to rewrite this, I would get, well, I would keep the 1/4 out here, and then secant theta is also the same thing as 1 over cosine theta, like I've said before. I'm gonna, instead of dividing by tangent squared theta, because tangent squared theta is also the same thing as sine squared theta over cosine squared theta, I'm gonna multiply it by the reciprocal just to make it easier. And when you do this, you should get cosine squared theta all over sine squared theta. And, oh, we forgot like I said before, I always forget the d thetas. So I would multiply by d theta. From here, the cosine, it will cancel out, the cosine squared theta will cancel one of the cosine thetas out, so then you would get the integral of 1/4 times it by cosine theta all over sine squared theta d theta. And then if we were to take another look at this, we can see that we can use u substitution. I want to try to get rid of the cosine theta d theta. So then in this case, I would say that u is equal to sine theta. Du is equal to cosine theta d theta. The cosine theta d theta cancels, is also equal to the du. So then I would get 1/4. I'm just going to multiply this by 1. The sine squared theta is also equal to u squared, and then I'm just going to put the du out here, just because it makes it easier for me. And I get 1/4 all over, this is 1 over u squared, the same as u to the -2 power times it by du. And just like Calc 1, we would say that 1/4 is equal to, now we can use the Calc 1 approach, and we can say that u to the -2, we're gonna add 1, u to the -1 all over -1, so then this would just be 1/4 in brackets, 1/4 times -u to the -1, the same as 1/4 times it by -1 over u. In this case, our u is equal to sine theta, so we get 1/4 of -1 over sine theta. But we want to get the thetas back into the x, so we would say that -1 over sine theta is also the same thing as cosecant theta. So from the beginning, we know that x is equal to 2 tangent theta. If we were to rewrite this form to get just theta, we would get theta is equal, I can just rewrite this as first, x over 2 is equal to tangent theta. To get just theta, I would say that tangent inverse of x over 2 is equal to theta. If I were to draw this out using SOHCAHTOA, tangent is equal to opposite for the x over adjacent, which would be 2. Using the Pythagorean theorem, you would get that this one would be the square root of 4 plus x squared. And we're looking for the sine theta. Sine theta we would get is equal to, so that's opposite x all over hypotenuse. Hypotenuse is along the side, x over the square root of 4 plus x squared. Since we're looking for the reciprocal, we would see that because we're getting negative 1 over sine theta, I'm just going to pull out the negative to the 1/4, so we get negative 1/4 all over times it by cosecant theta. We're going to get the reciprocal, so then we're going to get this is equal to negative 1/4 times it by the square root of 4 plus x squared all over the bottom over the top, because we're getting the reciprocal, all over x. If we simplify this out, we're going to get negative square root of 4 plus x squared all over 4 times x. And that should be the answer to this integral up here. The second and last question was true or false, the integral of 1 over the square root of 9 minus t squared dt can be made easier to evaluate by using the substitution t equals 3 tangent theta. Well, if we were to look at this table of trig substitutions again, we would see that this 9 minus t squared fits the format of, I would say, a squared minus x squared, this top formula, and that would give us x equals the square root of 9 is 3 sine theta. So in this case, instead of 3 tangent theta, it would be 3 sine theta. So then the answer to this question would just be false. And then that is it for section 7.3. I hope this helps.